Hey, good day. I am Jim Pytel. I'm an instructor at Columbia Gorge Community College's Renewable Energy Technology program. This is EET 121 Digital. Today we're going to discuss the system application of logic functions. If you remember from our last lecture here, we have, here's our first screen. Basically, this is the exact same thing that's on pages 17 and 18, and the book has a really good write-up, so use this as kind of an assistance to the book too. Definitely I recommend reading those pages on 17 and 18. But we'll walk through it. I'll hopefully clarify a couple of points that are not necessarily wrong, but a little misleading. But if you remember from our, as confusing as this diagram looks like, if you remember from our logic functions here, our list of logic functions, we've got a comparator, our arithmetic operations, code conversion, our encoder and our decoder, and I'm actually going to go ahead and put this thing in here. Let's see, our regular straight up converter, code converter. We got our data selection, multiplexer, demultiplexer, our data storage with flip-flops, registers, semiconductor memory, magnetic and optical. We've got our counters, and that is all we discussed. So we're going to put a bunch of these things together and actually do something with it. And what we're going to do, the example in the book, is a aspirin factory. And basically all it's going to do is using our basic functions, like, so we've got a counter right here. So basically there's a sensor at this valve right here. And anytime a piece of aspirin falls through, that's a little aspirin, falls through, it sends a pulse on it. And it goes to the counter. And basically what it says, it's just going to add on to there. So it was previously at 49, a little pulse comes along, now it's at 50. So what it's going to do, it's going to send this data to A right here, into the adder. Additionally, that same data is transferred to the B input of the comparator. Okay? So we're going to stop. I'm going to kind of draw, actually let's draw in red. I'm going to draw a red line right here. It's kind of two parts to the system. Above this is kind of the human interface. Below this is the machine interface. So even though we started with the machine interface, we're going to go back up to the human interface here. And I'm going to draw those things in blue. So basically what we've got here, the human interface portion of it, we've got an operator at a keypad that types in the number for, okay, how many we want to fill our bottle to. The example is 50, so it says 50, types in 50. Basically it does the code for 50, the encoder codes it, and it sends it to a register A. And basically all that is doing here is going to split up. It's going to pretend that there's two different, it's like there's another further block here. So this here is one system that doesn't speak the language of this system. So there has to be a code converter here. And basically that code converter is going to take that data and put it to the comparator of A. Over here, it's going to send from register A. It's going to go to the decoder, which just changes the display 50. So all this portion of it, all this thing does here is just display what you type in there. This, however, here, the code converter, basically, if you see here, remember our comparator has three outputs. A is greater than B, A is equal to B, A is less than B. All we really are concerned with right now is this guy right here, A equals B. We want to know that. Because when A equals B, if you remember B, right here, is the number of pills that are in the bottle already. So if A equals B, that means we've got it. So let's stop the valve. There's a little stop valve right there. So once we've stopped the valve, basically there's going to be no more aspirin that needs to be filled into this one. But what we need to do is do some form of machine interface here to advance the conveyor belt. Basically, that same signal, when A equals B, it's going to send back out, and it's going to go to the conveyor belt and to the stop valve. So it stops the valve, and then it goes ahead and advances the conveyor belt, and then this guy, this little bottle, is gone. and then this guy moves forward, and that resets our counter. So there's another, so basically that A equals B does three things: stop valve, advance the conveyor belt, and reset the counter. So counter's back at 0, and then starts the whole thing over again. Now, you also want to know exactly how much aspirin in the whole system-wide thing. Like how many aspirin have I put into this thing totally? We've got this system right here is on this side. We've got an adder. Basically, all it's taking is, remember, there's two outputs to an adder: a sum, carry out. Sum, carry out are being sent to this register right here. Full screen. So now this register is what I did to make this thing a little bit clearer. I know in your book it has a B right here, but I put total because there's already a B right there. So no sense in having to. You can name anything you want to. I don't know why this stuff there, but standard B. But anyways, register B is being refed back into here because those are the two numbers to add. Because anytime you're adding, the last bottle filled to the total, you got to re-add it to it. Okay. So now the register total here is, this is just because we want to use all our functions here. So we've got a code converter total that goes to, again, this is a different system, they maybe don't talk the same language. They go to decoder here, and then that goes to a display, and it says, example, it's 550. And now, just because we want to use all the functions, we want to do data selection. We'll do a multiplexer and say there's a number of aspirin machines that are putting all their data into this multiplexer, and over a single line, like a telephone line. And what's the last thing you need for a multiplexer? Is our clock signal, or sequence control. And it's being sent out to a remote location where a demultiplexer splits it up between the other computers it needs to talk to. So yeah, definitely read pages 17 and 18. Super good explanation. And all I did right here was just change that B to a total, so that way you're not confusing it with this B up there. Okay, hopefully that clarifies page 17 and 18. And in the next lecture, we're going to go over fixed function integrated circuits.